Hello, everybody. Thanks for tuning in. Today, I'd like to give you an overview of the research that I'm doing in my group, which is called Safe Autonomy and Intelligent Distributed Systems Lab, SAIDS for short, which I'm currently leading here at USC. The way I'd like to do this, I'd like to talk about safe control of learning-enabled autonomous systems, which is one topic that my group is focusing on. I'll elaborate on this in detail, and I'll give you an overview of other topics that my group is also working on. So I'm going to talk about safe control of learning-enabled autonomous systems. First of all, what are autonomous systems? Autonomous systems are control systems that operate autonomously in complex and open-ended environments. They perceive the environment, they reason and learn from data using AI techniques, they assess risk and uncertainty, and they make decisions in order to achieve a wide variety of tasks. The specific applications in autonomy that I'm particularly interested in is in autonomous driving and robotics, and more recently also in wildfire prevention. As you can imagine, in Southern California, this is a big topic, as well as warehouses. But there are many more, for instance, in aerospace, agriculture, smart cities, or in healthcare. And all of these applications here certainly highlight the importance and the potential impact that autonomous systems research may have in the future. Over the past years, the wide availability of data coupled with computational advances in machine learning and AI has accelerated the progress that we have made in order to build these systems. And I've shown three examples here, Boston Dynamics robots, Tesla cars, or a drone fleet at the Kumar Lab, where these systems really perform highly challenging tasks with ease. And indeed, from these videos, one could claim that autonomous systems are a reality. However, the question that I would now like to ask is, do we really have all the theories and tools in hand to build autonomous systems that are also safe? And I would argue that the answer to this question is no. Simply because at the same time, we've seen a lot of failed demonstrations. We've seen Boston Dynamics robots crashing, Tesla cars colliding, and we've seen drone fleets collapsing. Even more so these days, autonomous systems are learning-enabled, and learning-enabled systems turn out to be fragile. For instance, if we think back a couple of years to 2015, we thought that by 2020 we would have self-driving cars. Evidently, this is not the case. Even worse, industry has reset their expectation from level 5 autonomy, so full autonomy, to only level 4 autonomy, meaning autonomous driving only in certain environments. So there are certain risks that are associated with this autonomous driving. And there's a recent example from Southern California where Cruise, a company, had to recall all their self-driving cars due to an accident that happened there. Now, what are the reasons for the difficulties that we're facing here? One is certainly that the way that we train our AI is fundamentally flawed, as we train and tweak our algorithms to lab-like environments and specific scenarios without generalizing to other scenarios and to the real world. Another reason is that neural networks or AI in general is fragile and easy to fool. There's a famous example actually from a couple of years back where we have an image of a panda and a classifier that correctly classifies this image. Once we put some small noise on top of the picture, the resulting picture to the human eye at least really looks the same, but the algorithm suddenly misclassifies it as a given. So algorithms make wrong decisions and they're not aware of the uncertainty that the algorithm has in a specific instance. Now, the question then becomes, how can we make these autonomous systems safer? But also, what are the fundamental control limitations that we're facing? And what are the performance and safety guarantees that we can provide? Now, let's zoom in a little and let's look at this block diagram, where we have a system, in this case, this is a car, that operates in an uncertain and dynamic environment, which the car perceives using sensors such as camera, LiDAR, or radar, together with perception and prediction algorithms to get state estimates of the system and of the environment that are then to be used within a planning and controls module to compute controls input to close the loop. Okay. So what are examples here of learning-enabled components? For instance, object detection. We could have prediction here, for instance, predicting pedestrians at an intersection. We could have machine learning for system identification or even for control itself. Now, a couple of challenges that I would like to talk about here in this loop that I'm specifically focusing on is the complex environment itself and the perception with high-dimensional sensors, which certainly requires uncertainty-aware and reactive control methods. The learning-enabled components themselves are a challenge. As argued, they're fragile. So what we need is robust training, but more importantly, verification of these components, potentially in an online manner when integrated into the closed-loop system. We may not only have one learning-enabled system, but we may have several learning-enabled systems that interact with each other. So how can we do distributed control? And we may need new system specifications for systems that operate in such an uncertain world, in unknown environments, and with the uncertainty that learning-enabled components bring. So I argue that we need dynamic formal languages that can reason over uncertainty. And we have these days photorealistic simulators, we have high fidelity models, and we have sometimes more, sometimes less data. But how can we use these to mitigate the sim-to-real gap? And lastly, real-time computation. We want to do all of this fast, and therefore we need efficient computational algorithms. Now, my research focus on the design of verifiable control frameworks for autonomy, along with efficient computational algorithms. And my group, more broadly, focuses on these 5 areas, one being data-driven control. So I've thought about how we can learn control laws from expert demonstrations. And one other thrust in my group is on statistical system verification. Here, for instance, runtime or online verification. How can we, during the operation of the system, predict that the system might potentially enter failure modes? I've also worked on multi-agent systems, such as temporal logic constrained multi-agent systems, and more broadly on formal methods and control. So how can we design control algorithms for systems under formal specifications? And how can we maximize different notions of robustness, for instance here, temporal robustness? And lastly, risk-aware autonomy, how can we make decisions under uncertainty? And this is what I'm mainly going to talk about today in more detail. And at the very end, I'll give you highlights of the other parts of my research as well. So in summary, my research provides a formal and computational approach to systems and control theory. In my research, I use theories and tools from control theory, formal methods, and machine learning and AI, as well as applied statistics. And as you can imagine, I work at the intersection of these fields. But really the glue that puts these fields together in my research is optimization and different notions of robustness. The specific topic I'd like to talk about today is safe control in dynamic environments with conformal prediction. And a little bit of formal methods you will see in the end. And as I mentioned before, this is basically the research that I've been doing in my group over the last 2 years. Okay, so what's the problem that we want to solve today? We would like to compute control inputs for a system so that the system avoids dynamic agents in the environment with a probability of at least 1 minus delta. So imagine that you have a car over here and you would like to compute control inputs for the car so that it avoids other cars and pedestrians in the environment. Why is this a challenging problem? Well, first of all, the dynamic agents, they may be stochastic and have unknown intentions. What one usually does is one may use complex learning-enabled predictors. However, as we saw before, these may be fragile. So how can we get uncertainty quantification for the dynamic agents as well as for the learning-enabled predictors and integrate them into control? It's a challenge. Some existing work that I don't want to omit here, you could use vanilla motion-based planners, for instance, graph or sampling-based. However, these typically ignore dynamic agents. You could also use reactive control methods, navigation functions, dynamic window approaches, or control barrier functions. However, as these are reactive, they don't use any predictions and typically consider simple systems. And more recently, there have been works on predictive, interactive, and non-interactive methods, for instance, DeepRL or Gaussian process-based modeling and control. However, these rarely bring safety guarantees, or they have to make simplifying assumptions. So how can we quantify uncertainty of learning-enabled predictors and design safe control laws? Now, I would first like to talk a bit more broadly about learning-enabled systems and how we can reason over their safety. And one big challenge here is how do we reason about their safety when they're high-dimensional? And by high-dimensional, I really mean that we have deep neural networks in here, so networks that have several layers and that may contain of hundreds or thousands of neurons, right? So analytically analyzing this closed loop is difficult. There are existing works. for instance, satisfiable modulo theory, solvers or mixed integer linear programming techniques, or even hybrid systems reachability. However, these techniques face scalability issues, and you certainly cannot use them during the runtime of the system, so during real time. On the other hand, there are relaxations, for instance, convex relaxations like semi-definite programs or linear programming relaxations, or even compositional approaches. However, these are usually overly conservative, and you also cannot use them. So ideally, we would like to navigate this trade-off between scalability and conservatism. And additionally, we would like to reason over randomness that enters this loop. For instance, disturbances on the car, noise on the sensors, or the dynamic environment itself that brings inherent randomness. And we were asking ourselves, can we instead use efficient statistical tools to formally reason about safety of learning-enabled systems? Now, what we argue here in this line of work is that what we need is an online monitor that we integrate into this loop and that represents uncertainty via efficient statistical abstractions. So the idea is really statistical uncertainty representations and safe control to do this using a statistical tool that's called conformal prediction. Now I need to tell you a bit more about conformal prediction, as you may have not heard about it, and I'll do this in a nutshell. So conformal prediction has become very popular in recent years. In fact, there was a keynote talk on it in NeurIPS in 2020. And it has become popular because it can do uncertainty quantification under minimal assumptions. So what I mean by that is it's distribution free. Assume you're given an input-output pairs in a supervised learning setup that is drawn from a distribution calligraphic D, then we don't need to make any assumption on this distribution. It could be any funky distribution. It doesn't have to be Gaussian. At the same time, we don't need to make any assumption on the predictor. For instance, if you have a predictor mu that takes an input and estimates an output, it could be a neural network again. However, what we need is we need the availability of an IID calibration data set. So a set of input-output pairs that are also drawn from this distribution calligraphic D. Now, the goal in conformal prediction is the following. Assume that we fix a failure probability delta. Then you would like to compute a prediction region C, such with probability of at least 1 minus delta. A new test data point Z is contained within this prediction region C. Just to illustrate this, assume you're given 3 images, shown over here, again, along with a classifier. Okay, and the images are of varying difficulty. Here, the first image is easy to classify, and the prediction region C only contains 1 label. Okay. However, the picture in the middle is already a little more difficult, and it contains, in this case, 4 labels. And the third image, the most difficult one, contains 6 labels. Okay. Okay, so how does conformal prediction work? It's all based on a quantilemma. So this slide is a little more mathematically, so I'll try to walk you through it slowly. Assume that you're given k+1 IID random variables R0 to Rk. These are typically referred to as the non-conformity score, but you can just think of it as a prediction error. Now, the goal is to find a probabilistic upper bound of our test data point R0 in terms of the calibration data R1 to Rk. In fact, what one can show is that, again, with a probability of 1 minus delta, it holds that R0 is bounded by the 1 minus delta quantile over the empirical distribution of our calibration data R1 to Rk and infinity added. So how does this look like? Well, we simply plot the histogram of our calibration data here. So on the x-axis, we have the values of R, and on the y-axis, the frequency. And then we take the 1 minus delta portion of it. So, well, how can we compute this quantile? Well, we just compute this number. So we take the ceiling of k+1 times 1 minus delta, this is p, and we take the pth smallest nonconformity score. And this is something you can compute really efficiently. Okay. One comment, there's an implicit data requirement. So since we take the pth smallest nonconformity score, you need that p is smaller or equal than the number of calibration data points k. And just for an example, for a regression, you can choose the non-conformity score to be the error between the output and the predicted output. And then you know that the prediction region is centered at the prediction and has a width of 2 times the quantile. I argue that conformal prediction is really useful in control and more generally in robotics because it's simple, general, and efficient with the right non-conformity score. A small example that we did in a paper here, I don't want to elaborate too much, but we were predicting cars at an intersection that could go left, right, or straight. So there were 3 modes, and by setting up the right choice of the nonconformity score, our prediction region could capture this multimodality here, and we could even fit ellipsoids to tightly encounter these modes of driving left, right, or going straight. Okay, so now that we know a bit more about conformal prediction, we can use it for safe control in dynamic environments. Now, our work is motivated based on 4 observations. If we look at these 3 examples, then we know that, well, the system dynamics in these examples are well understood and can be modeled. So we can model cars as bicycle dynamics with potentially friction, and we can also model mobile robots. That's really not the problem. However, the dynamic environment is uncertain and in general hard to model. But these days, we're living in a data-rich world, so we have large data sets that describe the behavior of environments, right? And along with that, we have learning-enabled prediction algorithms that work really well. So we want to use the system dynamics data along with learning-enabled predictors here with conformal prediction to design safe and computationally efficient control algorithms. Let me first give you an overview of what we propose here. Assume that you're given an offline trajectory dataset. And let's make this specific. Let's pick an example. Assume you're at an intersection and you have pedestrians that you want to avoid by driving a car, right? So you have an offline trajectory dataset of pedestrians crossing this intersection. Now, during the operation of the system, so online, you observe the position of the pedestrian up until time t. So you know y of t minus 1, y of t minus 2, and so on and so forth. And then you use a trajectory predictor, for instance, a long short-term memory network or a recurrent neural network, or for instance, also more classical approaches like Kalman filters, to predict the future behavior of the pedestrian, here denoted by y hat of t plus 1, y hat t plus 2, and so on, right? Now, the important question is, how good are these estimates really, right? We learned before predictors can be fragile, specifically learning-enabled ones. So we don't really know how good these estimates are. So what we're doing is we're running a conformal prediction step on top with a goal to compute prediction regions, here shown in blue. And these should be valid. And by that, I mean, with 1 minus delta probability, it should hold that the pedestrian is within these regions. And then we forward these regions to the robot where we know the dynamics and where we want to design a probabilistically safe controller. Specifically, in this case, we design an MPC, a model predictive controller, where we enforce that a safety constraint C is imposed on the system X and the environment Y is non-negative with high probability. The contributions here are computationally lightweight algorithms along with probabilistic safety guarantees. And we also show how we can extend the work to temporal logic constraints and how we can deal with distribution shifts. Okay, so first thing I need to do is I need to tell you how we can do uncertainty representation in dynamic environments. So let's go back to our example where we have pedestrians and we model them as random trajectories. So we say that y0, y1, and so on is drawn from a distribution calligraphic D here. And this is a fairly general modeling framework. For instance, it captures discrete time stochastic systems such as MDPs. Consider then that we have a trajectory predictor that maps all the observations that we have made up until time t to predictions of the future of the environment. And we do so until a mission horizon capital T. For instance, these could be social LSTMs. So an LSTM for each agent, and these LSTMs then communicate with each other. But we're not limited to social LSTMs. This is just something that worked really well in our case, but you could use any other predictor. And then recall that the task was to compute these prediction regions shown in blue over here. So a naive approach to do that would be the following. So I'll present a naive approach first and then a more efficient one. So we set up for each time tau that we predict into the future, we set up one nonconformity score that is basically the prediction error predicted tau steps ahead. So in this case, we take the ground truth at time tau steps ahead, and we compare the error with the prediction tau steps ahead. And then we apply conformal prediction in a slightly modified manner. So we don't take the 1 minus delta quantile, but instead we take the 1 minus delta over capital T minus T quantile. So we do a slight correction here. And we do so in order to get multi-step prediction regions. So we want that for all times tau that we predict into the future, we want that for a new test data point, the prediction error is bounded by the quantile c tau. Okay. Now we implemented this in CALA, an autonomous driving simulator, where we have pedestrians that start at random positions and go to random goal positions at random speeds. And what we did is we trained an LSTM here, and we plot here the histogram of the 2.5 second ahead prediction error. So on the x-axis, you see the error, and the y-axis, the frequency. And importantly, what you see here in green is the size of the prediction region for different final mission horizons, capital T. And you see as the mission horizon grows, the prediction error becomes larger, okay? And you can observe the same thing for a 4-second ahead prediction error. So the observation here is that the size of prediction region scales with the mission horizon T, and this is, of course, something undesirable. So the question is, can we do something better? So recall that the reason why we're conservative is basically this modified quantile that we're computing here. And we can avoid this if we set up a nonconformity score, only one and not several nonconformity scores now, where we instead take the maximum over all prediction errors of the future. So these are the RT plus ones and of capital T over here. And we multiply them with a normalization constant that I'll elaborate on the next slide. So for now, you could just think of it as those being set to 1. Now, what we then have is if we compute the 1 minus delta quantile over these nonconformity scores, that for all times tau that we want to predict into the future, the prediction error is bounded by this quantile and a normalization constant that we use to renormalize here. And again, this holds with high probability. Now, I think it's best to illustrate this. We have a case study here where we have a pedestrian and we predict the pedestrian's position 20 time steps into the future, shown in blue over here. Then for the naive approach, the prediction regions are shown in red. They're quite large, while our max approach here, shown in green, is much less conservative. For instance, if we look specifically only at 1.25 second ahead prediction error, then we see here in blue test prediction errors. And we see that our approach, the max approach in green, tightly encapsulates 95% of the data. And this is exactly the coverage that we were aiming for. Now, one thing I haven't told you about and that I still owe you is how do we choose these alphas optimally? Okay. So what we do is we compute these alphas as the solution of an optimization problem that I've written down here, and I'll walk you through slowly. So the first thing we do is we enforce that this max nonconformity score is used. And then we minimize over the quantile, over the empirical quantile of this max nonconformity score. And additionally, we enforce some normalization budget that allows us to give some guarantees of the optimality of our problem, right? Now, importantly, this optimization problem is a mixed integer linear complementarity program that can be solved offline. So why is this a mixed integer linear complementarity program? Well, the quantile over here can be written as a linear program. So this whole thing becomes a bi-level optimization problem. But then we can rewrite this linear inner problem as using its KKT conditions. And then we end up with a linear complementarity program. And the mixed integer linear or the max operator here can be written as a mixed integer linear program. Okay. In our paper, we also show that if we remove the integer variables over here, we get a more efficient algorithm that retains some optimality guarantees. Okay, so now one can use these prediction regions and can simply design a controller. And the first thing to do would be an open loop control design. So we want to find an open loop control sequence U0 to U of capital T minus 1 that minimizes a cost function subject to dynamic constraints, input constraints, and state constraints, and importantly, a robust safety constraint. So we enforce that the safety constraint C holds for all states Y within our prediction regions. Now, how can we enforce this in practice, as this is another bi-level optimization problem? We use a Lipschitz constant reformulation. So we enforce that C evaluated at the prediction Y hat is lower bounded by the Lipschitz constant of C times the quantile capital C tau. And if we can solve this optimization problem, we find a safe controller with a probability of at least 1 minus delta. So let's look at a small toy example. Here we have some pedestrians and a mobile robot that plans around there. And at time 0, we make predictions, we compute the prediction regions, and the robot plans its path around and executes the trajectory. As you can imagine, this is potentially conservative, and it may even lead to infeasibility. So the optimization problem here may not even be feasible. So what we instead do is we use this optimization problem in a receding horizon fashion using a model predictive control. So now instead at each time, we recompute the control input by obtaining measurements of the pedestrians, by recomputing the prediction regions, solving this optimization problem, and applying the first control input. Okay. So what we're doing is we're solving this optimization problem at each step where we update this robust safety constraint, and where additionally we use a prediction horizon here. Now, if this MPC here is recursively feasible, we can show that we find a safe controller with a probability of at least 1 minus delta. Importantly, in a paper that got recently accepted that will show in presented L4DC, we show how we can modify this robust safety constraint, and under certain conditions we can show how we obtain recursive feasibility. Now, getting back to our toy example here, now you can see that at each time step, the agent recomputes the prediction region so that the path that the robot is taking is much less conservative. We also implemented this in Carla, and the first thing we wanted to do is we wanted to compare the theoretical guarantees we were guaranteed with the empirical observations we made. So we were here guaranteed to have a 99.83% coverage for the one-step ahead predictions, and empirically we found that we're slightly higher, in fact. When we ran the MPC for 100 times, we only monitored 1 safety violations, while we were guaranteed to have at most 5. And we also did a comparison with the Gaussian process. In fact, we found out that the Gaussian process that we trained here only had coverage of around 70%. Okay, so far we talked mainly about navigation specifications. So we wanted our robot to go from A to B while avoiding obstacles. But one may be interested in more complex mission specifications that we're here enforcing using temporal logic specifications. So for those of you that are not familiar with temporal logic is Boolean logic equipped with temporal operators such as eventually, always, and until. And while I don't want to go into syntax of semantics of temporal logics, I want to give you an example so that you can see how expressive temporal logic is and what kind of specifications you can impose on a system. For instance, this drone here, you could say always avoid region E, every hour inspect regions A and B, and you can have reactive specifications, such as if the battery level is low, then recharge eventually in C or D, and always between some time, turn on communication. Okay. Like I said, I don't want to go into details here, but we will denote temporal logic formulas by the symbol phi, and you can associate a performance measure rho phi with such a formula. And if this performance measure is positive, it means that the formula is satisfied, and more generally, the more positive the measure is, the better it is for us. So now what we consider is such a temporal logic task that has a performance measure rho phi that is defined over the system X and the environment Y. Okay. So to do control, we proceed as before. We predict the behavior of the pedestrians into the future. We compute our prediction regions here, but then it gets a little more tricky because our task specifications is now more complex and a temporal logic specification. So what we do here is we compute a robust performance measure, rho phi bar, that is defined over X and the prediction Y hat. So how does this look like? On a high level, we simply compute the worst case performance measure. So we take the infimum over all the states in our prediction regions and we evaluate the performance measure over it. Now, the control problem is, of course, that we would like to maximize this robust performance measure by picking the right control inputs. And we show in a paper here that is on arXiv already and that we're about to submit soon, that we can solve this problem recursively on the structure of this temporal logic formula, and it effectively results into a mixed integer linear program. Just a short example I want to show here. Assume that you're given a leader that is shown in blue and a follower shown in red, and the leader wants to reach these blue region within certain predefined time intervals while avoiding the obstacles. And the follower here in red wants to also reach this red region eventually within some given time interval. But at the same time, it wants to follow closely the follower as well with a given precision. And as you can see here, the agent achieves this goal, or the agents. Okay, so lastly, I would like to talk about distribution shifts. So what do I mean by distribution shifts? Well, it's simply when the design and the deployment conditions of the system or of the environment specifically may be different. Then we refer to this here as a distribution shift. What are examples of this? For instance, we could have collected data at an intersection close to a nursing home where we have mainly old people. And now we want to employ the algorithm close to a high school or to an elementary school where we have young kids running around and their walking pattern is certainly different. Okay. Another example is that we could have used data from photorealistic simulators, but now we want to employ our system in the real world. Okay, so in these scenarios, the framework that I presented before really has no safety guarantees. However, luckily, there are versions of robust conformal prediction that let us still deal with this problem. Here, in this case, assume that our calibration data is drawn from some design distribution, calligraphic R, and that our test data point is drawn from some deployment distribution, calligraphic R0. What we assume here is that these distributions are bounded in some suitable sense. Here we're saying that the F divergence between these two distributions is bounded by epsilon. And then what we know is from the literature that we can get very similar guarantees where our test data point is probabilistically bounded by C tilde, so not C, but some C tilde here, which is also computed as an empirical quantile, but now by using an adjusted confidence level that can be obtained as the solution of a set of convex optimization problems. Now, with this robust conformal prediction, we know that, or when one studies it, that we need more data. So it has increased data requirements. But one can then use it to do control design as well as verification, which we have done in this paper. However, what if the distribution shifts too much? For instance, if our distribution shift is more than epsilon, okay? So one can then use adaptive conformal prediction, where we build prediction regions online from an online data stream. In fact, how this works is we compute an empirical coverage over here that we have observed over the past data, so over the online data stream, and we compare it to our desired coverage level that we then multiply with a learning rate. And this is then used in order to update our coverage level that we use to compute the prediction regions. And we can then simply design an MPC using adaptive conformal prediction regions. And if this, again, under this assumption that the MPC is recursively feasible, we find an on-average safe controller. Specifically, we know that when the mission time horizon goes to infinity, we recover our 1 minus delta coverage, but now only when we average over the safety constraints over time. We implemented this on a drone that should avoid a flying frisbee. The frisbee has highly nonlinear dynamics and is subject to noise. And all I want to say here is, or talk about, is a comparison with existing work. We aimed for 97.5% coverage here. And in fact, we achieved 99.2. And the minimum distance to the frisbee was only 2.91 meters. While some competing methods here from one of my collaborators and an extended Kalman filter here achieve 100% success rate. So it's more safe, but it's overestimating the uncertainty. Recall, we're only aiming for 97.5%. And in these cases, the minimum distance to the drone was 14.2 and 5.27 meters, which means we overly estimate the uncertainty. And with our algorithm, the drone can fly closer to its performance limits. Okay, so this was the main technical part, what I wanted to talk about today. And this, like I said, was the past 2 years, or this was a project from my lab from the past 2 years. But I've also worked on other topics that I want to briefly highlight. For instance, on data-driven control. Assume that you know the system dynamics, or at least you know them partially, and assume that you're given a set of expert trajectories, here shown as these spaghetti trajectories, that are assumed to evolve within a safe set, calligraphic S here, this red box. What we then do is we feed both the dynamics as well as the trajectories into an optimization-based algorithm in order to learn a safe control law. Specifically, what we learn is a function that under-approximates the operating region of the expert trajectories, here shown in blue, and has the property of being forward invariant. So when we start in this blue set, we're guaranteed to be able to find control inputs to keep the system in there. Our algorithm here has formal safety guarantees, and we also show how we can handle perception uncertainty and how we can learn control laws for unknown and hybrid systems. For instance, I just want to show a couple of videos. We have an expert controller over here. In this case, this is just a PID controller that we use to unroll data, again in Scala. And from this data, we learn a safe controller, in this case, a control barrier function that you can see executed over here. And if you look there closely, you see that our trained controller closely approximates the safe behavior of the expert. We also learn safe controllers from dashboard camera images. So here we have a dashboard camera images in the simulator, and we compress the images to be able to deal with them computationally, and then use these images to train a safe controller. And you can see the results over here. The perception-based controller still keeps the system safe. We also learn controllers for hybrid systems. For instance, here we have a walker that walks down an inclined ramp. If you don't apply any control action to the walker, it will just fall down after a couple of steps. However, you can, in fact, actuate the walker in the hip and in the ankle. And what we did is we used an energy-based expert controller from Russ Tedrace's textbook to collect expert demonstrations. And we then trained a two hidden layer fully connected neural network. And the result is what you can see here. So the correct and control actions from this learned controller are shown in green, and we see that the system is safe. Another highlight from my research agenda that I want to talk about is on system verification. So specifically, I've worked on predictive runtime verification, where we assume that we have observed a partial trajectory of the system during its operation, during its runtime. And we would then like to compute the probability that a performance measure here, again, of a temporal logic specification is non-negative. Now, our framework here is the following. We again assume that we have an offline trajectory dataset of the system. And during the operation of the system, we again assume that we have observations of the states until time t. We again take a trajectory predictor to predict the system's future behavior. But then we evaluate the performance measure raw phi here on the observations and the predictions that we have made. And we have a similar issue. Well, we're asking ourselves, how good is this predicted performance? Like, is it a good estimate or not? And what we do is we again run a conformal prediction step. In fact, we have several algorithms that we propose here to compute a probabilistic lower bound of the performance measure in terms of the predicted performance and the constant C here, which is a measure of confidence obtained from our algorithm. Now, we evaluated this on in Scala again, where we trained two different learning-enabled lane-keeping controllers. We used an imitation learning controller that you can see here, and a learned control barrier function-based controller. And in this paper, we answered the question, first, can we even predict unsafe behavior of the system? And also, can we find the safest controller between the two of these? And lastly, I want to briefly at least talk about some highlights from my research agenda on both multi-agent systems and formal methods and control. So the broad problem that I worked on here is a controls problem. So we want to solve a control problem under temporal logic specification. So we would like to enforce that this performance measure raw phi is positive and that we potentially maximize it, okay? Subject to some dynamics constraints. Now, why is this a challenging problem? Well, it's difficult to solve in general because this performance measure is non-convex and non-smooth. And specifically, it's computationally intractable for multi-agent systems. So one line of work that I have designs integrated planning and feedback control methods. So the planner kind of decomposes the complex temporal logic specification into a sequence of simpler specifications that are then executed by low-level and time-varying feedback controllers by each agent. And my PhD advisor and I, we have written a book on this topic that's called Formal Methods for Multi-Agent Feedback Control Systems that's scheduled to appear in MIT Press in the Cyber-Physical Systems series in spring 2025. I've also worked on temporally robust control synthesis. I don't want to talk about this too much, but we controls engineers, we often talk about robustness in terms of tubes, for instance, tube-based MPC, right? But temporal robustness, as you can see here, may also be relevant in some applications, and we design temporally robust controllers. And with that, I'd like to thank you. I hope this was a good overview of the activities that are going on in my group, specifically also we talked about one of the topics in more detail. And if you're interested in my research, please feel free to reach out to me via email. And I've also listed the references over here that I mainly talked about in this talk, and the main collaborators that were part of the work that were presented in detail today. Thank you.